Hello guys, welcome back. Today we're looking at the AMC 10A 2022 part 2, and we're starting from problem 17. So for problem 17, we have obviously ABC is a repeated decimal with 3 digits repeating, and then that is equal to 1/3 of 0.A repeating plus 0.B repeating plus 0.C repeating. So obviously we all know how to rewrite these into fractions. This is just 99 over 1/3 A over 9 plus B over 9 plus C over 9. Don't forget the parentheses. And then we basically just do our thing, right? Literally, in the we just multiply both sides by 3. Or no, actually, hold up. It's 27 over A plus B plus C equals 999 over A, B, C. Obviously, right? We just distribute the property, and then notice that 99 is indeed divisible by 27. So after we divide, I believe it is to be, I think A, B, C over 37 is equal to A plus B plus C. So A, B, C equals 37A plus 37B plus 37C. And up to this point, I was simplifying A, B, C, but that's not actually what it is. It's not A times B times C. It's 100A plus 10B plus C equals that. And then we simplify even further, which those steps I'm not going to include, and we finally get 7A is equal to 3B plus 4C. Notice how 1, 1, 1, 2, 2, 2, 3, 3, 3 are obviously solutions to this, but there are more. There's actually more solutions symmetrical to 5, 5, 5, this order triplet of solutions, because for every 3 we increase C by, we have to decrease B by 4. So there's other pairs of solutions such as 4, 8, 1, 5, 1, 8, 5, 9, 2. As you can see, they're all symmetrical regarding 5, 5, 5, and eventually we get 13 ordered triplets of ABC. Okay, now on to problem 18. Okay, so we have a coordinate plane and we're rotating it. So first of all, we have to understand what we're doing each time. Each time we're rotating it counterclockwise around the origin. So say we have the point that we're trying to find at the end is 1, 0, so x equals 1, y equals 0. We're rotating it counterclockwise, so this way, n degrees, k degrees, and then we're reflecting it across the y-axis. So, and then we reflect this, so it was rotated to here, and now we reflect it back to this side. And then we're not only performing this once, we're performing this transformation n times, t1 all the way through tn, and we're trying to find the least number n that makes the point 1, 0 go back to itself after a certain number of transformations. So first of all, we have to kind of, for this problem, I wasn't able to solve it during the mock contest, but according to the solution, the first step on these problems is just to kind of observe the pattern after a few moves. So let's see, after one rotation, it is 1 degree clockwise, and then it gets flipped, and then we rotate it counterclockwise again, but this time 2 degrees, and then we flipped it back, and then we rotate counterclockwise again, 3 degrees. So notice how after every 2 transformation, the point basically rotates 1 degree counterclockwise, right? Because after 2, we reflected it twice, so it is basically unreflected, and we basically just rotated 1 degree counterclockwise. So we had to rotate it 360 degrees to get it back to here. But since there's a reflection at the end of the last operation, we actually only have to make it 180 degrees, which means we only have to make it back to here. So that is only 180 degrees, and since we have to have 2 transformations per degree rotated, as we've already seen, we have to do 180 times 2, which is 360 rotations. However, that is not yet the answer, because we have not yet included the last transformation in which it gets flipped back. So we overcounted that one, and the answer is 360 minus 1, which is 359. Problem 19. Okay, problem number 19, we have 1 over 1 plus 1 over 2, dot, 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 equals h over L17, where L is the least common multiple of the first 17 numbers. And now we're trying to find h mod 17. Notice how if we commonize the denominator on the entire left side, it's just going to be L17, obviously, on the bottom. However, on the top, we're going to have L17 over 1, L17 over 2, dot, 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 which is equal to L17 over h, and of course at the end, sorry, L17 over 17. And realize the bottom obviously cancel out. I mean, not cancel out, we can just multiply L17 on both sides, so basically cancel out. And then notice that since we're only trying to find, since H is equal to this thing, and we're only trying to find H mod 17, notice how all of these first terms doesn't matter at all, because L17 is a multiple of 17 for sure. So when a multiple of 17 mod 17, of course, it's going to be 0. But only in the last case, 17 is divided out. So we only need to find L17 divided by 17. We only need to find that mod 17. So basically, it's 1 times 2 times ... times 16 mod 17. So we just use some modular arithmetics, and it is easy to find. I believe 5. Yeah, 5 is the answer after some simple modular arithmetics. Now problem 20. I would say relatively this one is a little bit more straightforward. We have a 4-term arithmetic sequence, x plus a, x plus a plus x plus 2a plus x plus 3a, right? That is the arithmetic sequence. And then we have y plus yb plus yb squared plus yb cubed, and that is our geometric sequence. The first 3 terms of the resulting sequence is 57, 60, 91, and now we're trying to find the last term. So the last term, the first terms are just going to be x plus y, right? X plus a plus yb, and x plus 2a plus yb squared. So we're basically trying to find x plus 3a. Why did I write 3? X plus 3a plus yb cubed is equal to what? Using these first 3 equations and the result that we know they get us. Obviously, just like always, when we have a system of equations, we try to subtract them. So call this 1, 2, 3, if you can kind of read my handwriting. 2 minus 1 is going to give us a plus yb minus y, which is equal to a plus y times b minus 1. And then we can also subtract 3 by 2. And in case you're wondering through the contest, how do I know which to subtract, really is just intuitive, because those two look kind of close, those two look kind of close, and you're just trying to mess around with it until you get something closer to this. So 3 minus 2, obviously you get a plus yb squared minus yb, which gives you yb times b minus 1. And of course we forgot the a. And then notice how equation 3 and equation, I can't even read, equation 4 and equation 5 are also kind of similar. So how about let's try subtracting those as well. 5 minus 4, that is going to give us y b minus 1 minus y b minus 1 is equal to, oh wait, yeah, we haven't even wrote the result. Those are 57, 60, 91. So this top equation will give us 3. This bottom equation gives us 28. So when we subtract them, give us 31, and when we subtract them, we get 28. And then notice how the bottom equation can be furtherly inverse distributive property. Y times b minus 1 squared is equal to 28. And obviously, there's only 2 squares that are divisible by 28. It's either 1 times 28 or 4 times 7. So just some quick check and guess and check. We can find that the final answer for the last equation is, this part is just going to be 206. I'm pretty sure you guys all know how to do that after we reach this step. Now problem number 21. Okay, number 21, it is a pretty difficult problem in my opinion, but I did think of a big brain way to solve this that is, I'd say, rather different from the solutions. So solutions, either you extend the line and do some very hard to understand fancy stuff, or you kind of cut or fold in the triangle, whatever they said, and then somehow without even proving, it goes that the little triangles on the side are right triangles. But I did, however, think of a smart way to prove that the right triangles, even though it being a 3D solid, is still going to be right angles. We have to think about it this way. We basically have, let's ignore the 2 other hexagons first and just consider 2 of the regular hexagons, and they're basically connected like this, right? They are both regular, except, well, imagine them being tilted to a little angle. And then we know that one side is 90 degrees. That's the bottom side, right? It's 90 degrees, and let's just see. Imagine this is a square with 4 90-degree angles, and there's 2 other invisible hexagons that we're ignoring here. I'm just gonna draw it. That we're ignoring here, and we just need to find this angle. But the solutions, obviously, if you looked at it, it says that this is 90 degrees. But if you don't want to look at a very fancy extension and stuff, and you still want to kind of prove why it's 90, the idea that I'm giving you is because it's just like, imagine we place this side on the ground. Then it's basically, then if we look at it from side view, turn this whole thing over, hexagon 1, hexagon 2, of course these 2 angles are going to be the same. Whatever this angle is, it's just going to be this angle, because this is the ground. We're placing this edge on the ground, so whatever this angle is going to correspond to this thing. Isn't that kind of a smart way to prove that since this is 90 degrees, this got to also be 90 degrees? So, well, knowing that, it's simple from there. We have 1, 1 on the side. So since this is 90, there's a 45, 45, 90 triangle being 1, 1, and root 2. So we have side length root 2 up here. And the octagon is just going to be a not very regular octagon. But we know side length being 1, 1, 1, root 2, root 2, root 2, root 2. And we just got to kind of find the area, which is easy from here. So isn't that kind of a smart way to prove that this is 90 degrees? That's how I thought of it. But I doubt that I'll be able to do that actually during the contest, because, well, I went from the conclusion of that being 90 to finding the proof instead of the other way around. I don't think if I try to just prove it without knowing that it's supposed to be 90, I'll be able to do that. But anyways, moving on. Problem 22. Problem 22 is also a fun problem that I solved by myself because I just kind of like combined thorax problems. We have cars 1 through 13, and then we're arranging them and we're picking them up in increasing order. And there's a concept called number of passes, and we're trying to find the number of arrangement of cards such that there's we pick them up in exactly 2 passes. So notice the number 2 is pretty unique, because 2 passes is not 3 passes or 4 passes. 2 passes is when we basically set the pass of the cards by just choosing the what cards we select on the first pass. And to help you understand that, let's say the example, say 1, 2, 3, 4, 5. If we already know that the first pass we're going to be picking up those cards, and we know there's going to be blank spots in the middle, like say those spots are blank, we know what's going to go into these spots for sure, because there's only 2 passes, and we've already determined what the first pass is going to be. These has to be 6, 7, 8, 9, etc. So knowing this, we basically are just choosing X spots out of 13. It's just 13 choose X, depending on how many we pick up on the first pass. So it's just going to be the answer 13 choose 1 plus 13 choose 2 plus 13 choose 3, etc. 13 choose 12, I believe, or 13. One of these two. Yeah, 13 choose 13, my bad. Anyways, this whole thing is going to sum up to 2 to the 13th power. If you know some combined thorax, this thing is just 2 to the 13th power, which is 2 to the 10th, which everyone knows is 1024, times 2 to the 3rd, which is 8, which gives us 8, 50, I believe, 52, hold up, I'm a moron, 8192. Anyways, that is not, however, the answer, because notice on each of these arrangements, out of the 13 choose 1, 13 choose 2, 13 choose 3, there is exactly 1 in each of those that is just picking up in one pass, 1, 2, 3, etc. to 13, with no gaps at all. We just pick it up in one pass, which is not what we want. So we have to eliminate that case in each of those. So there's 13 total of those cases. So we have to subtract 13. However, notice also that we didn't include 13 choose 0, because technically summing up all of these won't be 2 to the 13th. Summing up 13 choose 0 plus 13 choose 1 plus etc. 13 choose 13. That is what's going to give us 2 to the 13th power. So we didn't include 13 plus choose 0, which is 1. And then we also need to subtract 13 for each of these 13 terms. So it's 8192 minus 13 minus 1, which is 8178. Okay, this is actually all I'm going to do for today. So today we went through problem 17, I believe, from 17 to 22, 6 problems. I think that's good enough for one day. And in part 3 of the AMC 10A 2022, I'm just gonna be finishing whatever we haven't done today. Anyways, yeah, I think I did pretty good today. And oh yeah, I should probably do a grind report, just like I did during the January USCO grind. So there is a local math contest in my state. Actually, no, 2 local math contests that's coming up in 2 days and another one in 3 days. And I'm barely gonna have any time to study tomorrow. So today I'm just like kind of cramming a bunch of math because I also did terrible on the math competition last Saturday. So I just mocked the AMC 2022 10B, I believe, and got a terrible score, but that is okay. I did a bunch of problems. However, I did not have enough time to go over all the solutions. I'm gonna be doing that tomorrow, and hopefully I have time to post more videos tomorrow. Thank you for watching, and I'll see you